goal is to collect drone-based data to evaluate how good new satellites are going to perform for this ecosystem. I'm an associate professor in the Department of Geography at McGill University. I've been here for 16 years, and I started the Applied Remote Sensing Lab back in 2008. I'm looking at everything from biodiversity to gas exchange to understanding the structure, the geology.
I've been a collaborator with Dr. Margaret Kalaska since forever. It's a pleasure to work with a person with such a vision, being one of the youngest scientists to come to McGill as a professor in the Department of Geography.
Since I've been at McGill, I've been looking at different kinds of remote sensing applications for environmental science at different scales. So we start from satellite imagery at the really broad scale, airborne, and then very small scale, sort of in situ measurements as well. Our current main focus is on the use of drones for various questions. We started seeing the need for higher spatial detail, but very large spatial extent data sets. Having that spatial registration and spatial accuracy is very, very important. When we first purchased the P1 and the L1, it came with a trial license of Terra. And we thought it would be really interesting to try processing software that was actually made for the sensors themselves. And then we started working with Terra at that time and saw that the output was actually really accurate. And so we stuck with that product for the processing. So it's a beautiful day today, so we're going to head out to the Mer Bleu peatland, and we're going to collect some photogrammetry and LiDAR data to help us plan for our next hyperspectral mission. So over the last 10 years, we've been using different kinds of remote sensing data to map the peatland in terms of its vegetation characteristics, as well as develop models where we relate data in terms of how the gas exchange is happening with the imagery that we get from drone data as well as from satellites. Mer Bleu is an 8,000-year-old bog. It's a site that is a calibration site for optical satellites. It's a really well-known, well-documented site.
They're a key ecosystem in terms of climate change. They've been storing carbon for hundreds and hundreds and thousands of years.
For us, it's a very important ecosystem to understand how it's going to react to changes in temperature and in the precipitation regime. We use both photogrammetry and LiDAR to create very high spatial resolution surface models of the microtopography of the peatland. Both with the P1 and with the L1 LiDAR, we're able to capture the small 20 to 30 centimeter elevation changes of the vegetation and really understand the spatial distribution and the areas where the mosses are exposed to the surface. But we also use it as a base layer for acquiring other kinds of data.
They are highly efficient and safe systems. They have safety redundancies that are key for us.
Data accuracy is fundamentally important because we're trying to relate these data sets to some other data set, whether it's from a satellite, whether it's ground measurements. So whatever we produce has to be correct not only within the model itself, but the model has to be in the right location in space. We can collect a large area of LiDAR and within minutes it's processed. And it's processed in a way that's actually usable right then and there.
Easy to implement workflows in the field allows you to check the data. Once you come back to the office, you already know you have good data sets, and those workflows are fundamentally important to overcome the cost of some of these implementations in the field.
Even in its most basic form, generating the outputs of the point clouds or the orthomosaics or the 3D models, those were great. And I think that's a unique aspect of the whole DJI ecosystem, that you're starting with a very accurate drone with the incoming correction with the base station. That actually information makes it into the data products. So then when it's processed in Terra, it's a highly accurate product.